metamaterials. And it seems that not many people know what metamaterials are, what they can do, and how they can work. So I want to just give a brief overview of what we're doing there. So quantum optics with metamaterials, and then move on to sort of cover some of the work that I was supposed to talk about last week, but we ran out of time. So I'll be coming back to that later on in the talk. But what's the unifying theme between the first half and the second half of the talk is the fact that we're looking for quantum, sort of new kinds of quantum effects in materials that are essentially made of very thin films. By very thin, I mean subwavelength. So these films will typically have a length of about 10 nanometers compared to the wavelengths of the order of 800 or 1,000 nanometers that we use in the experiments. So that's one feature, in fact, the very thin films. The other feature that we've been looking at is loss. So loss or dissipation is typically considered to be a problem whenever you try to do anything quantum. But it can also be seen as a resource on the one hand, as I'll show you in the first part of my talk. But on the other hand, it is also something that when you build a proper model, for example, a quantum field theory model for your system, you need, if you're going to do real experiments, often in optics, I think up to date, I think always in optics, loss has just been neglected because it's an issue. But actually, when you include it, it can give rise to its own contribution and is interesting in its own right. So first of all, there's some people working in my group and collaborators. Sasha Boltasev and Vlad Shalaev have been providing us with some of the materials, and a lot of the measurements have been performed in collaboration with Miles Paget's group in Glasgow, and some of the metamaterial work is in collaboration with Nikolai Zelodev from Southampton University. So the first thing I want to talk about is our work, what we've been working on, again, going back to this idea of absorption of very thin films, and in particular we've been looking at the notion of coherent absorption using known states. And this arose essentially from a first paper by Nikolai Zelodev, where I'm not sure actually, so we can kind of go through this here. This is an older paper of ours, but the idea is that you can create sort of a Sagnac-like interferometer where and Nikolai Zelodev's first experiments were purely classical, and with a single photon interferometer, actually you repeats just obtain very similar results as expected. So we can consider this for purposes of like a classical interferometer where you have two counter-propagating beams here. So laser, beam splitter, two counter-propagating beams. This is where we put our 10 nanometer freestanding metamaterial. I'll come to that in a moment. But essentially, you create a standing wave pattern. And similarly to what Marcus was showing us earlier on, depending on where you put your freestanding nanometric film, you will have interaction or you'll have no interaction with the standing wave pattern. So if you assume, for example, and this is why we were using a metamaterial in the first place, because it can really very precisely tune its properties. And if you take if you tune the properties so you have exactly 50% absorption, what you find is, if you go through the maths and also if you do the measurement, as you can see here, when the film is placed in a node, there is zero interaction with the oscillating electrical field, and the absorption disappears, goes to zero. You have 100% transmission. Okay, this is both with a classical beam and with, in the case of a single photon interferometer. If, on the other hand, you put it at the antinode of your standing wave pattern, then you, instead of the 50% absorption that you measure in the traveling wave case, you actually find 100% absorption. Okay, so this is why it's called coherent perfect absorption. 100% absorption, which in a 10 nanometer film is rather remarkable. There's no other way that I'm aware of that you can achieve this. The role of the metamaterial, you can see it's by metamaterial, what we mean is that there's a class of materials. So on one, so if you look at naturally occurring materials, you can have materials which can be tuned or are different because they're different at the microscopic level, okay? The distribution of the atoms and molecules make up the difference of why you have a chalkboard or a piece of wood. Or you can also then change the macroscopic properties of material and therefore make a chair or a table. But there's a place in the middle where you can make these metamaterials where you are still fabricating, these are man-made, and you're fabricating structures which are sub-wavelength in dimension. So each of these little resonators, like horseshoe-shaped resonators, are of the orders of 100 nanometers or so. So they're still wavelength, sub-wavelength size. So they don't give rise to individual sort of like scattering effects, but they can heavily modify the properties of the material. Okay, and it's by tuning these resonant structures that you can very precisely tailor, for example, the specific reflectivity, transmission, and absorption of your film, and therefore add sort of some functionality to what nature provides us. Okay, so now the interesting thing that, I mean, we originally did this because it wasn't clear, at least in my mind, how this coherent perfect absorption was working. So we said, okay, let's try and do this at single photon level. Does it still work? The answer is yes. I guess the interesting take-home message here is that although absorption is a probabilistic effect, here you can enforce a deterministic 100% probability of absorption of a single photon. But then what we did is we moved on to do this with higher order Noon states. So with states where you have, for example, so you have an interferometer where you have on the two arms a 2,0 or 0,2 state. And then you can ask yourself, what happens in this case? And it's less trivial. So the setup essentially is, so last week people were talking about Hongo-Mandel interferometers. Okay? So you have, here you have a BBO crystal which generates two entangled photons, although entanglement is not essential here. The essential ingredient that you need for Hongo-Mandel interferometer is indistinguishability, not entanglement. So let's just stick with indistinguishable. So you generate two indistinguishable photons, signal and diether, you separate them out, and then you recombine them on a beam splitter, and at the output of the beam splitter, due to the Hongo-Mandel sort of bunching effect, you'll get, in the two arms here, you'll get a 2,002 state. Okay? And then I cascade a second Mach-Zehnder interferometer after the first interferometer, and I re-interfere this Noon state onto my, what is here indicated as a beam splitter. That beam splitter is my 50% lossy metamaterial, okay? We've also tried other materials, so we've used, for example, graphene layers, which also work, but less well. So in this specific paper, we're actually using graphene. So this is just going over the setup again. So at this beam splitter, here you see this Hongo-Mandel dip that we were talking about last week. And the point is, so you want to work sort of this region here, because this is where you're having your bunching between the photons. And then here is where we're placing, again, our metamaterial or sub-wavelength absorbing film. Okay. So the interesting thing here now is that, so with a single photon, you essentially just reproduce what you get with the coherent state. In hindsight, that wasn't too surprising. But now if you go and look at what happens with a Noon state, things become less trivial. So in the lossless case, so if you had a perfect lossless beam splitter, that second cascaded interferometer essentially at the beam splitter either gives you back your, depending on the relative phase between the two arms, it will either give you back, it will act as an anti-Hongo-Mandel beam splitter, so it will just give you back what you had at the very input after your crystal. It will give you back a 1-1 in the two arms. Or if you have the other phase, it will just give you back again your Noon state. Okay? But if you have a lossy beam splitter, then things change. You can either, depending on the phase, get back. So remember, we're sending in two photons, so now on average, I'm expecting to have only one, on average, I'm expecting to have only one photon come out. But if, depending on the phase, I can either have a 1-1 coming out, or I can have this other mixed state here, where here on average, you see, you still have two photons, but I also have this state here where I have 0 coming out, okay? And I'll come back to later on to why I find this very interesting. It's, of course, extremely difficult to measure because there's no way to measure 0 photons. You measure clicks, you don't measure absences of a click. But if you could nail this down, essentially what this is saying is that with 50% probability, you have a deterministic 100% absorption of both photons at the same time, okay? Now, in optics, the only other process that I know of where you can get 2-photon absorption is a nonlinear optical process, and usually that involves very high intensities, and you have to beat the sample quite hard in order to have an appreciable sort of cross-section for this process. But here at the quantum level, we only have 2 photons, and I can enforce, just by fiddling around with the phases in my interferometer, I can enforce a deterministic absorption of 2 photons at the same time in the material. And that's something quite new. So these were our first measurements actually using graphene. These are sort of the reference measurements where we're taking all of the counts combined together and there's no oscillation. But if you go and look at the coincidence counts, then you see this oscillation here as you translate the nanometric film through the standing wave pattern. And you can nail this down. The only reason why this can appear is because indeed you have this term here, which is killing some of the coincidence counts and giving you this 2-photon absorption. But at the time, we didn't have precise enough measurements, nor was the sample good enough for us to really sort of nail down exactly what the coefficient was in front of that 2-photon absorption. So in the meantime, we've been repeating these measurements with a properly tuned metamaterial. You can see this is the same oscillation we were looking at before, now has a much higher visibility. And if we go through the maths, we are now able to really nail down the fact. Here you can see, so here's again, it's the data, and you can see these curves are fits from the theory with no free parameters. And that essentially then, in fact, there's no free parameters, it allows us to really nail down the sort of the number, how sort of the percentage of noon states that are actually absorbed at the sample through this 2-photon absorption process. Yeah? Yes. Yes. You mean which slide? So you're talking about sort of the phase difference between... this oscillation. Yes, there was some beating going on there. We're not sure exactly where that is coming from, but that seems to have disappeared. And if you repeat the measurements more carefully, that seems to disappear. I think that's an artifact. I'm not quite sure where that's coming. But in essence, so the theoretical maximum is 25%, and here we're measuring something of the sort of the order of 23, 24%. So the metamaterial is really close to ideal. We've managed to really nail down, essentially the only way you have to measure, the only way you can measure the complete absence of 2 photons is by making sure that you've measured everything else very precisely. So all the single counts, the ones, and all the other coincidences. So at the output of our, if you go back to the setup here, you see that we've got a 4-way coincidence detection system. And so you have to really make sure that you're measuring everything, and that you also characterize properly the input states. Okay, so why is this interesting, and why I mean, beyond sort of the curiosity of the fact that you can have a 2-photon absorption in a quantum state, what we're looking at is an idea which actually first proposed in this paper here. The title maybe isn't very illuminating, but the application is, summarizing the concept that's expressed here, is that, so there's quite a lot of research at the moment going on in trying to establish the role, or not, of quantum coherence in biological processes. And sort of the main process that people are looking at is photosynthesis. So it would seem that classical physics is not able to explain the efficiency of photosynthesis, And there's some belief that there's some kind of quantum coherence that's enabling the transport of electrons through these complex molecules, and therefore enhancing the efficiency. And the question is, can we measure that quantum coherence or not? One of the standard approaches to doing this is what is called 2D electron spectroscopy. I don't have time to go into the details of that, but the idea is that you're using very intense broadband laser pulses, and you're trying to excite the various transitions and then look at how these decay over time, and if you see any revivals, those usually can be ascribed to some kind of quantum coherence. What these guys did is they took a sort of one of these photosynthetic molecules, and the problem that people usually face is that you start from a ground state and want to get to some excited state, which is characterized by the excitation of two excitons, but you have to pass through an intermediate exciton state, which is very broadband and will tend to decohere very quickly. So the solution to that, using some standard lasers, is to use extremely short pulses. Okay, so that you can excite you can sort of transition from here to here in a very short time. So excite it, and then very quickly, sort of a few or some tens of femtoseconds later, come in with a second pulse, and then transition up to here. But then the problem is that this state here usually has an extremely narrow bandwidth. But you're using very broadband pulses. And so the efficiency of this process actually is on the one hand, is extremely low. But on the other hand, because you're using broadband pulses, here you have a whole array of levels, and you can't really select which of these levels you're exciting from here over to here. You just excite everything all together, and all you can measure is a sort of the final broadband overlap of all of these transitions. And this essentially boils down to the fact that for a standard laser source, you're limited by the fact that delta omega, the bandwidth, times delta t, the duration of the pulse, has to be greater than 1. But within entangled photons, you don't have that constraint anymore. You still have a delta omega delta t relation, but now the delta omega is actually given, it turns out it's given by the bandwidth of your pump laser, not of the individual entangled photons. And if you use a CW laser, that can be extremely narrow bandwidth. So in other words, you can make sure that this transition here is resonant with the narrow line width of your laser and have an extremely sort of high efficiency of excitation here, and you can also very selectively choose exactly which transition you pass through to get to this. So this is kind of summarizing, again, this concept of classical light. The two pulses are limited by this relation. You have a overlap of broadband pulse and absorption line. You don't have this relationship with entangled photons. Okay? The final superposition really depends on the bandwidth of your pump laser. This is the key point here. And now, so in this work, they were proposing. They went through the details of what happens in, I can't remember the name of the molecule. I'm not as good as Marcus is remembering the names of molecules, so I won't attempt to do so. But the problem is that to do that experiment, it's rather hard because the molecule is what it is, and you have to find a laser with exactly the wavelength, which is determined by the molecule. So the idea was to try and test the concept using an artificial molecule, so using a metamaterial resonance structure, which can now be tuned to be resonant with typical lasers that are available in the lab. And so here we've designed our meta molecule, and essentially what we have here is this very broad intermediate. This is a plasmon now, it's not an exciton. The words change, but the physics doesn't. You have this very broad plasmonic resonance followed by a very narrow resonance over here. So the idea is that this resonance here would be on resonance with our pump laser, but using our two entangled photons, we pass through this broadband and then through a second absorption process of plasmon. So one photon will excite one broadband plasmon, and then this plasmon will absorb the second photon to reach this state here. And by using the techniques I described earlier on, where we can very precisely map out exactly how much two-photon absorption we have in our material, we should be able to demonstrate that as you fine-tune this peak away, for example, you move it away from the pump laser, you should see the efficiency of this two-photon process suddenly decay. So this is work in process. I was wanted to sort of share with you some of the ideas and some of the things that you can do sort of at the interface between optics and quantum biology. Okay, so in the second part of the talk, I wanted to speak a little bit about some of the things that I mentioned during the lectures last week, but didn't have time to finish off. And what we've been looking at is, we started off looking just at standard classical nonlinear optics, but now moving to a sort of quantum field theory effects in what are called Epsilon near-zero materials. So there's a whole new generation of materials, I'll talk about those in a minute, that have the real part of the dielectrical permittivity that's equal to zero. Now, that on its own is not sort of revolutionary. I mean, there are many situations where the dielectric permittivity, at least the real part, can go to zero. Think, for example, of a plasma. This is the plasma the dispersion relation, the electric permittivity of a plasma, and you can see that when the frequency of your light beam reaches the plasma frequency, this epsilon here will go to zero. And likewise, for example, in waveguides, it's well known that at the cutoff, well, in general, the epsilon is given by this relation here. This is just the background material, and this is related, like this D is the diameter of the waveguide. So this relation is essentially bringing together the material. You have a contribution from the material, you have a contribution from the waveguide geometry. But at cutoff, so given by this frequency here, so right at the edge of where you pass from allowed propagation to prohibited propagation, the epsilon zero goes to zero. Okay, so the fact that you can have a material with zero real part of the dielectric permittivity is known. It wasn't really that well investigated until recently. Now there's a whole community working only on this. Zero, in general, they're called zero index materials. Now, weirdly, so I don't have my phone with me, it's over there, but the point is even the materials that I'm going to be talking about in the next 16 minutes are also not new. And their electrical properties are very well known because they lie on the screen of all of your phones. They're what allow you to have a touch screen. Okay, so they're called transparent conductive oxides. They're transparent because you can see through them. They're oxides, they're not metals, they're semiconductors, and they're conductive. And this is what allows you to have your touch screen. So their electrical properties are very well known. The materials are very easy, so you can buy them off the shelf for next to nothing. But their optical properties, in particular their nonlinear optical properties, are much less well known. And we were very surprised to discover, we started looking into this last year, discovered that actually nobody had done some serious sort of nonlinear optical measurements on these materials. And so this was, these studies led to sort of two papers together. It was sort of, I'd say, friendly competition with Bob Boyd on this. He got into science, we got into PRL. Had I known. Anyway, so what's going on here? So we've got this whole new generation. Actually, it's not just on your iPhone you have what is called indium tin oxide, but there are also many other materials. So Bob Boyd was using ITO. We were using this other material that Shalev and Baltaseva gave us, which is aluminium doped zinc oxide. Okay. All of these materials have a plasma frequency at near-infrared wavelengths, so around 1300 nanometers, where you can easily do quantum optics experiments, for example, and also have readily available detectors. And it turns out that they have a huge nonlinear optical response. So how did we measure this, and where does this response actually, this huge response, come from? So we did a very simple experiment, pump and probe experiment. So you're pumping with very high intensities, actually, close to a terawatt per square centimeter. And then you're probing with a weak probe, and you're measuring simultaneously reflection and transmission. And if you do that, for example, standard ellipsometry measurements work in a similar way. From R and T, you can pull out the real and imaginary parts of the epsilon, and this is usually used just sort of in the linear optical domain. So if you just do a linear optical measurement, so you switch off the pump, you just look at what the probe does, you can measure the epsilon. You see the real part here crosses through 0 at about 1300 nanometers. The imaginary part, interestingly, is always extremely small. Okay? So metals also have a plasma frequency, but if you go and look at the imaginary part, it's huge, meaning you have huge losses. Also, most importantly, meaning that if you go and look at what the refractive index is, so the square root of this complex epsilon, the refractive index is also relatively large. But the key thing here is that the imaginary part is there, but it's small. The refractive index of this guy around 1300 nanometers is about 0.1, which is rather weird, right? I mean, the vacuum has an n of equals 1, and here you have a material with an n which is 0.1. It's quite close to 0. Then one can start asking questions in terms of what does that mean for the speed of light if I'm still to take that to BC divided by n, for example. Okay, so coming to the nonlinear optics, as I mentioned last week, the delta n, the change in refractive index that you can induce with a pump pulse, is given by this coefficient, n2 times the intensity. The n2 is given by this chi3, that's a number, okay? It's a dielectric susceptibility sensor term. But it's divided by the refractive index. And I've just pointed out that the refractive index can be tiny, okay? So your nonlinear effects, the nonlinear coefficient itself is chi3 isn't enhanced, but the n2 is simply due to the fact that it's roughly given by chi3 divided by n, and n goes to 0. The effect is going to explode, okay? And if you plot out just the numbers, we don't need to go through the equations here, but you can see that you can analytically predict that there will be a resonant-like, although it's not a resonant effect, but you have a resonant-like effect enhancement in the real part of the n2, and you also have an imaginary part which actually goes through 0. So we did the measurements with the pump and probe. For the sake of the interest of time, I'll move on and show you directly the results, which are summarized in this graph here, where you can see this is the red curve is the theory for our sample, and the blue the measurements. You can clearly see that we have an enhancement around the epsilon near 0 wavelength. But the key point, the key take-home message here, is that if we look in terms of what the actually measured delta n is, because that's the physical quantity we're measuring, let's forget the n2 and the chi3. For what I'll be talking about in the following 10 minutes, what is important is the delta n, okay? And that's huge. It's of the order of 0.5. Remember, we're starting off from a background of 0.1. So what that means is I've got a refractive index, which is n0 plus delta n. This term here is much larger than this term. And even that on its own is weird, because the whole concept of nonlinear optics is usually based on this perturbative approach, where this term is always much smaller than this term. And indeed, that's the case. If you go and take fused silica glass, for example, and ask yourself, what's the maximum delta n I can achieve? It's usually of the order of 10 to the minus 3 maximum. And then after that, you start damaging the material. And here, all of a sudden, we have something which is 2 to the orders of magnitude larger, and puts us in this non-perturbative regime. And again, I think there are some very interesting questions there. We need to really go back to the textbook physics and try to rewrite how you actually derive these nonlinearities in the first place. So the refractive index changes of the order, you can see here, of the order of 500%. I won't go into the details of this, but what I did want to point out is that these measurements here are showing that the imaginary refractive index change is actually playing a large role. And we'll come back to that in a moment. And that also gives us a link to the first part of the talk, where I'm saying that you have to include losses into your model. Okay, so what is the model that we're interested in? Why was I doing all of this in the first place? Because what I've been developing, as you probably gathered from last week's lectures, is I've been trying to sort of develop analog models for gravity, but in general, not necessarily just looking at black holes, but generic spacetimes, and trying to mimic these in the lab. And what we can do with this kind of material, what I was looking specifically for when I I started looking at these materials was to see if there's a way where we could create a space-time that is spatially homogeneous but expanding in time. Okay, so I completely drop any spatial dependence and just look at the pure temporal dependence. And essentially what we have here, what these results are telling us, is that I have a material, and remember I'm pumping this with a laser pulse. So if my laser pulse has a duration of say 50 femtoseconds, then this delta n, the refractive index, is going from 0.05 all the way up to 0.5 on a time scale of about 50 femtoseconds. So if I have a broad pump pulse, so I can consider it spatially uniform, I have essentially an n of t where that n is changing very violently and on a femtosecond time scale. So, and the idea then is that there's, you can use this to study quantum field theory in expanding spacetimes. And I would also argue that in this case, it's no longer an analog. Okay? When we were talking about black hole analogs, those really were analogs. I don't have a real black hole in my lab. I'm just mimicking the space-time and looking at how test particles and photons propagate in that metric. But here, I would argue I have the real thing. I mean, there's no need for that expanding space-time. I mean, the most famous example of a spatially homogeneous space-time changes in time is, of course, cosmological expansion. Okay, so, for example, these inflationary theories all rely on this kind of effect. And one of the predictions is indeed that the early inflaton field, for example, experience sort of amplification of the initial quantum fluctuations, which then lead to seeding the dishomogeneities in the universe and the formation of galaxies and so on. But we don't need to go there. We can just stop at the idea that we have an expanding space-time that is spatially uniform, is changing in time. Okay? We don't need to really pull in the analog of cosmological analog. So in that sense, I'd say that this is not an analog, but it's the real thing. Now, I wanted to, very, very briefly, because it's not the main thing I wanted to point out here, but I'll just very briefly go over for the benefit of people who weren't here for last year's lectures, over these two claims. So the first claim is that a time-varying medium leads to a time-dependent frequency of any propagating waves inside that medium. And then as a corollary to this, a time-dependent frequency implies particle, or in our case, photon production, always. An unavoidable consequence. I won't do a proper sort of mathematical derivation of this. I'll just give a hand-waving analogy of why this has to be so. So what we're looking at here is, so the standard sort of situation, we're all very familiar with this, for example, is just a piece of glass where you hit the boundary and omega does not change when the light beam goes through a piece of glass, but its k vector does. What we're looking at here is something which is spatially uniform, but it changes in time. So it changes everywhere in time. And in this case, what I'm saying is that the k is constant, so the direction of the beam does not change, the momentum doesn't change, but the energy or the frequency does. And in this case, we have a space boundary. Here we talk about a time boundary, we switch on refractive index change. So it's relatively easy to say see that this time dependence is the time dependence that leads to frequency change. Just take your electrical field, write out the phase, the standard way, kz minus omega t. Your k, of course, is given by d phi and dz, and the omega is given by minus d phi and dt. So what does the dk and dt do? How does the k vector change when I have a change in time? Well, I can just rewrite this as dt and dt of the d phi and dz, just substitute it in here. Then I use this relation to write this as minus d omega and dz. But omega, I know, is kc divided by my refractive index. So if I plug that in and then just switch the differentials, I end up here with this dn omega over n times dn and dz. But I said this was spatially uniform. There's no z dependence. So that means this is equal to 0. dk and dt is 0, meaning that k is not changing through the time medium. If I do exactly the same calculation for my d omega and dt, I end up with this relation, minus omega over n, dn and dt. But this is precisely what I'm looking at. I have a dn and dt that's non-zero. So in other words, this leads to a time-dependent frequency, and omega does change. Okay? So now let's look at this a little bit more detail. This claim, a time-dependent frequency implies photon production. Rephrased, a quantum harmonic oscillator with a time-dependent frequency necessarily produces particles. Okay? And as I was pointing out, sort of hinted earlier on, this is a very standard result actually of quantum field theory in curved spacetimes, and lies at the basis of cosmological particle production, the dynamical Casimir effect, and even Hawking radiation and Roux radiation. You need to be a little bit careful about how you rephrase the time dependence in each of these cases, especially Hawking radiation. We discussed this at the tutorial last week. But essentially, this is the mechanism that lies at the basis of all these effects. So we're running out of time. So very quickly, one way to see this is, let me just go to the picture. You can start from, imagine you have this very standard, very well-known case where you have a spatially dependent potential, okay? And you know exactly how to describe the scattering in this process. You have an input wave, then you have a reflected wave and a transmitted wave. And essentially you would start from this equation from your harmonic oscillator, assuming that D minus V is greater than 0, okay? And then you can write out the solution. You have sort of some input condition, some output condition, and we can then write the input condition as we normalize to 1, we send in, we have a reflectivity and a transmissivity. But when we go to the time case, we can just take this exact very standard picture that we all understand how reflection transmission works, and now flip, exchange x with minus t to put myself in the time domain, okay? And when I do that, I have to be very careful at how I choose my input and output modes, because now I can't have the equivalent of that reflected mode, because I don't expect to see a mode which is propagating backwards in time towards minus infinity, so from a potential before that has even actually changed. So I have to change things around, and I end up having to keep, I have an input condition, and I have two outputs on this right-hand side. And it's really, this is the key difference when passing from x to t. Okay? I cannot expect solutions that propagate backwards in time at the input. And it's this breaking in symmetry, if you want, it's the arrow of time that is forcing me to make this choice. And in doing so, it changes it. So I have my input wave. I just rename these coefficients to use alpha and beta. And I'm doing this because these are the famous alpha and beta, so-called Bogoliubov coefficients. And I can derive what they are just by analogy with the previous situation. So this would be R over T. This comes out as 1 over T. And if I just rewrite my sort of energy conservation equation, R squared plus T squared equals 1, I get this relation for the beta, but using the fact that alpha is 1 over T, I get alpha squared minus beta squared equals 1. And this is the relation that tells me that not only do I have to have beta greater than 0, but every time I have beta greater than 0, I'm going to have amplification. Because if this grows, this also has to grow in order to maintain the difference equal to 1. Okay, and essentially the point is that beta greater than 0 is exactly, it's identical to saying that the transmission is less than 1 or the reflection is greater than 0 for a standard spatial scattering law. So if you're happy with the fact that a piece of glass reflects light, then you should be equally happy that a piece of glass that changes in time has to have beta greater than 0, or in other words, acts as an amplifier, and can also amplify quantum fluctuations. That's the essence of the problem. So I'll very quickly go through sort of these last results that we've been working on. We've just submitted them. So this is sort of the situation we have in mind. We have very thin film of this Epsilon near-zero material. We hit it with a laser pulse, and then we want to look at photon production in this expanding, time-varying space-time background. And the idea is essentially, so last week I was explaining sort of the recipe for calculating this. First, you need to identify your wave equation. So we can start just from the standard wave equation. We can rewrite this as a time-dependent harmonic oscillator. You take your plane wave input condition, propagate it. In this case, we have to do it numerically. Propagate it through this equation, and then you take the output states, nearly done. Take the output states, and you just project your output state onto a sum of these alpha and beta k waves, so positive frequency and negative frequency waves, and you calculate the beta, and from that, the total photon number is not equal, but it's proportional to beta squared. Now, if you do this for standard material, you get sort of what is a known result, and that is as you lengthen the time duration of this time variation, the peak emission quickly shifts to far infrared or even microwave or radio wave frequencies. Okay? It's roughly given by 1 over the time variation. And this number, remember this number is 10 to the minus 7, is also extremely small. When we go and look at what happens with our epsilon near zero material, here I have two graphs. One doesn't have absorption, one does. Let's just, for the sake of time, focus on this, in this case. What we immediately notice is that now the beta squared has gone up by 7 to 8 orders of magnitude. That's it's a massive increase, which is coming from this enhancement of the nonlinear response that I mentioned earlier. And really what we found really interesting is that the emission is now nailed down, regardless of our rise time, it's nailed down to the epsilon zero wavelength, which is also extremely handy because we can do measurements there. We cannot do single photon measurements at far infrared wavelengths. The technology isn't there, but we can do these measurements here. And if you go through the numbers, it would seem to appear, so what does this beta squared value actually correspond to? Well, if we have 100 megahertz repetition rate laser and a tau, so full width half maximum of a laser pulse of 10 femtosecond, so this is perfectly feasible, we have these numbers in the lab at the moment, we should have a photon pair production rate of about 10 hertz, which should also be measurable. And okay, I'll stop here. I'm done. Thank you. Lumen thin copy.
The nonlinearity, is it clear where it comes from? Would it also occur in pure indium oxide or pure aluminum oxide?
So there are two mechanisms. There are various mechanisms depending on the wavelength at which you pump. So people in the past have been pumping. The short story is you're generating a free electron plasma, okay, and that's where the nonlinearity is coming from. Now, where you generate that, whether it's an interband or intraband transitions, depends on the wavelength at which you're pumping. In our case, we are interband because with the relatively low photon energy that we have, you can pump in the UV and get. We're intraband. If you pump in the UV, you can get interband transitions. But essentially, and all the effects that we've been showing, I skipped through a couple of slides where there's some fits. Those were based on models, sort of the two-temperature plasma electron model, and fit very, very nicely to the results.
So the enhanced nonlinearity you talked about, it's also seen in coherently prepared materials.
It's seen also, sorry?
It's also seen in coherently prepared materials which undergo electromagnetically induced transparency.
Yes.
So you have enhanced Kerr nonlinearity at very low light levels. Mm-hmm. But it's over a very short frequency window because these are dealing with atoms with discrete levels which are very narrow. Yeah. So does it have implications for the QFT analogy which you have been?
So first of all, I would argue that in the so you're talking about cold atoms, for example, or rubidium vapors.
Rubidium vapors as well as cold.
But if you go and look at what the delta N is there, yeah, so that's what counts here, right? I'm not interested in necessarily enhancing the chi3 or the nonlinearity itself for that matter. All I'm interested in, what is the delta N I can achieve? And more than the bandwidth, what I would say is the limiting factor in those vapors is the delta N. It's still of the order, actually I think you probably have something of the order 10 to the minus 5, 10 to the minus 4. It's still extremely small. In order to see these effects, so these effects, I quickly whisked through the slides because of time, they need to be extremely fast, non-adiabatic, ideally, but they also need to be large. And this is why having this delta N of the order of 400% is so crucial. We've tried in the past with 10 to the minus 3, and you see, you go through the numbers and you see that.
I'm intrigued by your expanding space-time analogy experiment, but I was curious, trying to get a more traditional quantum optics picture of what's going on. It seems to me if you imagine sort of four-wave mixing between photons on different sides of the frequency spectrum of that 10 femtosecond pulse, you don't get all the way there. Are you thinking of a much higher order process? Or?
No. I think if you want to sort of have a sort of a reconduct this somehow to some standard picture, as you're saying, just think of what happens in your BPO crystal. Because you have a relatively thick crystal now. Remember, we're extremely thin film, but we come back to that. And then you have your pump wave, which is passing through the crystal, and have many oscillations. And what you do is you describe this as a parametric amplifier. Correctly so, because you have this oscillating pump field, which interacts with an oscillating signal and dipole. Okay?